So a very good afternoon. I know a very tiring day for a lot of you. It's almost 4:30. Everybody would be tired. So we'll try to keep it as simple as possible. And what I'll be discussing will be domain wall engineering in artificial spin ice systems. So let me quickly move to my main slide. So let me try to let us discuss what do you mean by frustration and spin ice system. In today's world, I believe everybody is frustrated, but how do we define it in the magnetic system? It's the inability to satisfy all interactions simultaneously, and it arises due to structural disorder or maybe geometry. And to understand the geometrical frustration, we will firstly be considering the entoferromagnetically interacting spins in 2D. So if you see this third spin, it's always in a confusion state whether to align antiferromagnetically with this spin or this spin. So the energy is never minimized. We move to the 3D structures, which is entoferromagnetically interacting spins. And again, it's like the third and the fourth configuration now are ferromagnetically aligned. So this system won't have a minimum energy state. Different microstates would be possible. And where do we observe this? Naturally. So this is naturally observed as spin ice materials, which were discussed in today's talk. Spin glasses as well were discussed. So spin ice systems, basically pyrocorols, which are the naturally occurring spin ice systems. So the question is why they are called as spin ice systems. So basically they have got a name from ice systems. These water ice basically have this tetragonically arrangement of hydrogen and oxygen atoms, where two hydrogen ions are nearer, and two are posing outwards, so they are farther. So this dysprosium ion have a very high magnetic moment of the order of around 1.5 Bohr magneton, which results that each of this dysprosium ion acts as a macro spin, right? So as it is shown in this figure, that it is acting as a macro spin or rising spin, where the two spins you are seeing are pointing inward and two are pointing outward. So this is also like the water ice system are having 2 in 2 out system, 2 in 2 out configuration, and hence they have got it name as spin ice systems. So in these systems, it was clearly given about the emergent magnetic monopole. What is this? So as I've already told, these are rising spins. You can see where this tetragonically sharing spin have 2 in 2 out configuration, and similarly this has 2 in 2 out configuration. So what we consider, if we see this here, the head we are considering as a north pole, while the tail we are considering as a south pole. So which have a plus QH charge and a minus QP charge. This is known as dumbbell model. So when you have slight perturbation in your system, you see this spin has flipped. So there is a generation of charge at the vertex where all your 4 spins are meeting. So this is generation of charge, a plus Q charge and a minus Q charge. And how? They are calling it as monopole and anti-monopole, which are connected via Dirac string. So these were the following possibilities of these systems were very interesting, obviously, but what was the problems in these systems? We could not actually naturally control the lattice parameter or the fluctuations or any other. It was difficult to control this necessary. So Wang et al. Came up with an idea of artificial spin ice systems. What are artificial spin ice systems? Basically, they are artificially manufactured degrees of freedom using lithography and nanotechnology. So with the help of nanotechnology, we are ensuring that these systems have the very strong shape anisotropy. When I talk about very strong shape anisotropy, so they will be governed by dipolar interactions. This is one of the zoom out in, we have considered the lattice arrangement, and this is one of the building block of this, which is the Y-shaped vertex, and it's clearly seen that they keep on fluctuating. So this keeps on, and this is the frustrated system, and the energy is not going to minimize. If we consider the number of degenerate states in this system, so you see that the first one which I have considered, this is 2 out 1 end, then again 2 out 1 end, and 1 in 2 out. So 3 possible degenerate state. Next, which I'll be showing you, it's 2 in 1 out state, 2 in 1 out again, And finally 3 out or 3 in, which is unfavorable energy states and difficult to secure. So they will be having a charge of minus qm, plus qm, and minus 3 qm or plus 3 qm. Obviously the last two states which we are talking is very, very unfavorable. So our aim was, if we could study the domain wall dynamics. We know domain wall have a lot of interesting features in it. We know domain wall, today we are talking about quantum bits. So is it possible to have quantum bits as means domain wall can accept the charged material? Yes, of course. So moving towards it, there were recent work which shows one of the array. These are the MFM images where they're showing that the magnetization reversal occurs via domain wall, and these domain walls act as source of magnetic charge, and these are non-biased random walk. Non-biased, what it implies? What it implies that it's not going to be a probabilistic event. No, it is going to have that the chirality of domain wall will decide the selectivity which arm is going to flip, and I'm going to show that in next slides. So similarly, there was one more work in which they said my chirality, what do you mean by chirality? I'll show in the consecutive slides, that the chirality of the domain wall will be the deciding factor for selectivity. And they also observed that in dynamic regime, the fast moving domain wall undergo Walker breakdowns. So let us, and also that they're going to oscillate periodically with the variation of these length of, if you see, this is kind of Y vertex which I'll be calling, and they're inserting domain wall and they're observing that which arm flips, your left or right, is going to decided by your chirality of the domain wall. So obviously I've already told you that domains wall they have a lot of implication in your neuromorphic artificial intelligence or your magnonics or reservoir computing. So it is important to study the domain wall. So let us try to understand how we can control the selectivity of domain wall motion and switching with defects in artificial spinized system, and can chiral selectivity switching be controlled? I don't want to have a chiral switching behavior. Why not? It depends on my geometry or my field driven. So we will like to study if we can control it using defects. So basically we employed many techniques to study the switching behavior. One of them was through mumex. This is the LLG equation which is shown, and other work which we did on square lattice was micro Hall magnetometry, where we grew Hall sensors on the heterostructures of gallium arsenide and L-gallium arsenide, and the stray field is detected by this 2-deck which gets two-dimensional electron gets, which when deflexes from the stray field is noted as the Hall voltage. So if the time permits, we will study this data, and today I'll be focusing on mumex work. So let's see how the time goes. Okay, so regarding the modeling, micromagnetic modeling, I've already told you we'll be using mumex. So let's understand bit of things, because here the nanobar dimensions would change my lot of things. So it is important to understand what parameters we are using. So basically I've used a 1000 nanometer disk with 100 nanometer. And these are the following, since we are using a permalloy nanobar, we are going to use this, and the damping was kept at 0.01. Okay, so what we have done, we have varied this angle theta. So varying this angle theta was the distortion, since this Y-shaped vertex is a symmetrical vertex. So everywhere the angle was 120 degree here. Now if we change the symmetry of the object, what is going to happen to the domain wall dynamics? Okay, so I told you what we will do. Now we will insert a domain wall here, and I have defined two chiralities, down chirality and up chirality. If you would have rotated your system like this, so the central one would have pointed down, the red one. So that would be down chirality, and this is the domain wall with up chirality. If you rotate this clockwise, you will see that the center one is pointing up. So this is how I am defining up chirality and the down chirality. Okay. So let's understand the effect of distortions. Basically, I have inserted my domain wall. This is an example of up domain wall, and this is basically, you see, it had a first of all 2 in 1 out configuration. We have perturbed the system with the domain wall, and we have distorted our system, a symmetrical system, by distortion, by rotating this axis symmetrically by 5 degrees, 15 degree and 13 degree. And let's see how with the change of energy barriers the domain wall dynamics will change. Okay, so we first initially tried to understand the reversal behavior of all the distortion we have changed, and we found that the coercivity and the saturation magnetization, it remains unchanged with distortion. But when we talk about the remnant magnetization, it is clearly visible that it is decreasing as my distortion angle is increasing. So that is really clear with, you see that the vertical, when we take the vertical vector sum of all my magnetization, that is removing, right? So that will cause a reduction of remnant magnetization. Secondly, one of the reasons that could be for reduction of the remnant magnetization is that no more my energy is not symmetrical, so there will be partial flux closure, there will be demagnetization, enhanced demagnetization field, which will be causing the reduction in remnant magnetization. But it does not tell us, understand why the domain wall will switch. So let us move and try to understand first the switching behavior. Okay, so this is the domain wall dynamics at 24 millitesla. What we have done, we have inserted the domain wall here, and we have applied a field of 24 millitesla in the upward direction. So this is for 0 degree Celsius. I'll just show you how my dynamics is changing. Just a second, I'll just play the video. So you see that initially my domain wall that's nucleates to vortex structure, and there is always a transition between vortex and intermediate domain wall states. The chirality first it injects goes opposite. I'll repeat the video. So it's not playing from this. Okay, yeah. I'll play from here, yeah. Okay, and finally, near the vortex, we see that the domain wall chirality has changed. It enters the leg 2, and finally it is causing switching of leg 2. Now, depending on whether I have up or down, I see switching. When you had your magnetization in the left side, your left leg, that is the leg 1, is switching. If you had your magnetization in the right direction, it's your leg 2 switched. So it's a chirality driven switching mechanism which is deciding which leg is going to switch at undistorted system, which is my 0 degree angle. Now I move to 5 degrees distortion. We see that it is same behavior. Even at 5 degree, you see with your magnetization in this end, this is your leg 1 which is switching. If you consider your magnetization or the down chirality, it's your leg 2, it is switching. So 0 degree and 5 degree have the same switching behavior. Now we move to 15 degree. We see that this is at at up chirality, it is following the same behavior. Yeah, so it is behaving very similarly, that with your up chirality, it's your left leg, which is similar to 0 and 5 degree. But you observe that with your down, it is also this leg 2 which is switching. So 0 to 15 degree, we said that the magnetic switching behavior remains same. And when we move to 30 degree, we see that the up domain wall didn't cause any change, your only undistorted leg switched. But when we consider the down domain wall, it's no more my distorted leg 2, it was my leg 1 which switched. This was the first transition we observed, that at 30 degree, the down domain wall switched my leg 1 instead of leg 2. And what we will imply that the chirality rule breaks down at 30 degrees. So let us remember one of the things, because I'm going to consider the energies to find out what has happened. Can I control the dynamics? So please remember this, that at 30 degree distortion, the chirality rule did not exist. There was no path selectivity. Okay. So now we'll move to the higher Zeeman field. So I have just shown you with the inset that this is not following my 15 degree or 5 degree rule, right? The chirality rule has broken. Okay, so now let's move to the higher Zeeman field. So again, with the higher Zeeman field, the switching was multiple switching. It was not very similar to 24. So let's see what happens at higher Zeeman energy. It is seen that at higher Zeeman energy, basically there is splitting of my domain wall. So when my domain wall switch, it's just not leg 1 or leg 2, it's both legs have switched, whether we are considering an up domain wall or a down domain wall. Okay, we now move to 5 degrees. So there is a mixed state switching. My 0 degree or 5 degree distortion have the similar kind of nature, where we have observed that the domain wall is actually splitting. It is moving both to leg 1 and leg 2. So there are of course formation of transient states, complex magnetic states, vortex domain wall components. So they was happening. So whether you had a distorted leg or not, it's both the legs which started switching. Now we move to a higher degree of distortion, that is around 15 degree, and what we observe that if you see 5 degree or 0 degrees, it was your distorted leg was switching and your leg 1 and leg 2 both were switching. But now if you observe, only my leg 1 has switched, not the leg 2. Similarly for down domain wall, it's only leg 1. The undistorted system is remaining unchanged. And 30 degree we observe the similar things. The undistorted magnetization remains similar. There is no switching which was observed for both leg 1 and leg 2, that has gone. So there was an anomaly at 15 degree that only leg 1 switched instead, and 30 degree we are saying that it's a chirality driven switching. Okay, so in fact the chirality has reversed. Now let us try to understand why it is happening. So just take away from my two presentation that at 24 millitesla, basically we observe wherever is your up domain, if the magnetization is in this direction, leg 1 is switching. If it is down domain, it's your leg 2 is switching. So similarly, that's the key behavior, and we observe that at 30 degree there was a break of chirality. Okay, so now we move to 42 millitesla. We remember that because of the higher Zeeman energy, we saw that 15 degree, regardless of the chirality, it was always my undistorted leg switched, and for 30 degree, leg 1 switched instead of 2, and there was a chirality reverse process. Okay, so let's compare the energetics of this system. So this is for 24 millitesla, and we observe that my dipolar energy actually is decreasing with increase in distortion, and the exchange energy is increasing with exchange of interaction. So that's very simple, because when you had clearly symmetric system, the dipolar in energy is very high, there is a magnetostatic coupling. Now that is getting weakened because of the disruption of symmetry, and when we compare all my exchange energies and Zeeman energy, we found that it's you can see clearly that the dipolar energies tends to decrease, exchange energy is particularly rising. So this is due to higher exchange energy cost, which is causing my system due to the distortion to increase further. Okay, so we now compare the annihilation time, the time in which my vortex core or my magnetic is actually causing switch. It is seen that with distortion at 24 millitesla, that is completely increasing. At 15 degree, I saw a very sharp increase, and that is finally decreasing. And finally, for 42 millitesla, we observed that Zeeman energy was very high as compared to my dipolar and exchange, but it showed similar trend, but dipolar energy remained almost constant. Your exchange energy remains almost constant. But switching time, we say that it is highest at 15 degree. And we know there was an anomaly at 15 degree. So let us try to further understand what is changing. It's different energies playing their different role. They are increasing, their distinct symmetry is broken. So let's try to understand. So what we did now, we actually, with the angle of distortion, we plotted dipolar energy versus exchange energy. So for this is for 24 millitesla. We know from 0 to, they were having very similar result from 0 to 15 millitesla, right? 15 degrees. But at 30 degree, we saw that your chirality was broken, right? So when we compare this ratio, it has fallen to 1.72. Only 5 minutes. Okay. So, so we see this ratio 1.72 is playing a very much transition role. Let's quickly compare the energies for 42 millitesla. We compare this is ratio of dipolar versus exchange, dipolar versus Zeeman, exchange upon Zeeman, and Zeeman was higher here at 42 millitesla. So basically when you have 0 degree, 1.89, I told you 1.8, right? So that's a very high strong dipolar field, no change. When we move to 5 degree, it's again 2, no change, because when your dipolar to exchange energy is so high, it's your chirality which was deriving my switching. But when I moved to 15 degree, that is now the RDE ratio is 1.94, but my D by Z and 0.5 are becoming very high. So this causes less distorted leg to switch first. Similarly, when I move to 30 degree, again this is now 1.72, lesser than 1.8. For 0 degree, 5 degree and my 15 degree, I was always getting a RD by E ratio greater than 1.8. So when it is 1.72, that's causing transition, and it's now reversal of chirality driven behavior. So what my energy ratio maps tells me, there will be 3 different reasons, chirality driven. When by R by D by E ratio is 1.8, if it is greater than 1.8, I am going to get a chirality driven behavior. But moment it gets below 1 D by E 1.8, either it's going to be field dominated or my geometry dominated. If the distortion angle is very high, it's the chirality or field which dictates the switching behavior, and if it feels behavior which will speak that the switching outcome will be independent of the geometry. So we made a very interesting phase diagram which shows that at lower field and lower your distortion, it's basically field driven, and when we have a ratio greater than 1.8, it's going to be a chirality driven switching. And finally, when you are moving to less than 1.8, it's going to be geometry driven switching. So in this way, we could say that playing with the distortion which changes your energy diagram can cause a change in the switching behavior as well as the domain dynamics, where everybody said that the chirality is the deciding factor of my selectivity, that has been broken due to the distortion which is now due to the symmetry broken. Okay, so we finally investigated T-shaped nanobar, and we see for 24 millitesla, you see that your domain wall is pinned. That is no more traveling, but at higher Zeeman energy, the wall releases, and we see that symmetry suppresses wall motion until your driving field crosses that critical threshold. So basically, it's when we have both the lengths distorted to a 90 degree thing, it's a very high energy barrier wall for the domain wall. Unless and until a very high Zeeman energy is applied, we will not be able to travel our domains wall. Okay, so conclusion to my slides, that this is the breakdown ratio 1.8. Moment you are greater than it, life is okay, chirality driven switching. But when we fall below 1.8, it's your ratio, this is the ratio of D by Z, dipolar energy upon Zeeman energy. So this will be a design parameters. I told you that this is for 1000 into 120 nanometer. When moment you change this aspect ratio, the value of this will be changed, and so we can tune this breakdown ratio. Okay, so geometric tuning delivers deterministic control of the domain wall, which is a very important tool. Today we heard about switchings, also switches, bidual switches as in the previous talks. So that is also necessary for these systems. Okay, so with this, these are the future scope, and I would like to thank my guide, postdoc guide, my students who are working on domain wall, and thank you everyone. So if there are any questions.
Thanks for that presentation. So now,
thank you for the nice talk.
Thank you.
See, in the pyrochlore lattice, you have 2 into 6 spins, and you are applying the magnetic field, and you are getting the monopole.
They'll not be, yeah, Dirac actually predicted.
How to know experimentally that in your
It is difficult. That's why these naturally systems were very difficult to control, all these systems, and that's why these artificial spin ice systems were designed to study the polarons or your dynamics. Now they are being used for logic gates as well. So
is there any other group to get this magnetic monopole instead of applying magnetic field? Any other pressure? Other thing that
yeah,
we
so
can get
XMCD people are trying to visualize. They are not true monopoles.
or not true?
They are not true monopoles. We know by Maxwell's second law that monopoles. So these are not true monopoles. In fact, I have few experiments where through MFM I have visualized yes, charge is stabilized, but overall the charge of the system is zero. There will be polarization effects, so they are not true monopoles.
And in real materials, why these spin ice systems are so rare? Because in intermetallic we have only one spin ice system, and so why these spin ice systems are so rare that?
No, there are a lot of work going on it.
Because in intermetallic we have only one, as far I know, that HIGG, that spin ice system.
Basically, there was also with people were studying noise spectroscopy on these systems, so it gets a bit difficult.
Nice talk, ma'am. So I was just wondering that you are referring as chirality. So chirality, is this vector or scalar spin chirality?
For my case, I am referring to like your basically in charge state. When you have these are single domain states, right? So you have one head to head here and other is up. So it will be having charges. So charges you can consider. They will not be. I don't think it will be vector. It will be scalar number.
Okay, so in a particular chirality state, you are referring it as a positive chirality or as a negative chirality?
See, for positive, you generally count it for plus Z for vortex core or minus Z, right? But I have a 2D system. There is nothing in the Z direction. These are my 2D systems. If you would have noticed, my thickness is 20 nanometer. And my nose spin is going to be pointing in the plus Z or minus Z. It's plus X or plus Y, whatever you consider.
Okay.
So these are shape anisotropic systems and hence no 3D. They are going to be a 2D dimensional of your spin ice systems.
Sunil, any more questions? Okay, if not, then let us thank the speaker.
When you say shape anisotropy, you mean the spins align along the surface of along the shape of the surface?
So what we like shape anisotropy I'm referring to as, if you've seen my these nanobars are very long. So it will ensure that all the spins are aligning in the same direction. So it will have a shape anisotropy towards the plus direction. And in fact, I'm using permalloy. So the magnetocrystalline anisotropy is very small for it. So it's basically now shape anisotropy which will dominate.
No, I understand same direction, but they lie in the plane of the...
Yes, there will not be deflection in the 3D direction, yes.
Okay, let us thank the speaker.